This question is about organic chemistry. Part A. This part is about two practical techniques used in organic preparations. Part 1. Complete the missing labels on the diagram and name the technique. So let's start with the missing labels. When we look at what's called a condenser, the most common mistake is mixing up where the water comes in and where the water comes out. So one way to remember is that you fill from the bottom and you see the water level rise. So that means that water in is at the bottom and water out is at the top. Then we have one more missing label, and that's the flask. So there are two different options for this. You could either say that it's a pear-shaped flask, or you could say it's a round bottom flask. Either would be accepted. The name of this technique is reflux. So this is a very common A-level technique, especially when making aspirin. To get the 2 marks for this question, you get your first mark for getting the water flow correct and saying that it's a condenser. And then you get your second mark for naming the flask, so either a pear-shaped flask or a round bottom flask, and naming the technique. That gets you your second mark. Part 2. Draw a labelled diagram to show apparatus set up for filtration under reduced pressure, or vacuum filtration. So the first bit of apparatus that we're going to draw is our Buchner flask. So because it needs to be a labelled diagram, we're going to label this as a Buchner flask, and we need to label from the sidearm that says to the vacuum or to the pump or even reduced pressure. The most important thing when drawing this Buchner flask is to draw this sidearm. Then we need to draw the Buchner funnel. So this funnel is going to be sealed with a rubber seal. It's important to show that it is going to make contact with the Buchner flask and there's not going to be any air gaps. So labeling this the rubber seal, and then we can label the Buchner funnel. So making sure that it looks a bit more like a funnel, and then we can label Buchner funnel. So if you're not a great artist, it doesn't matter. Don't spend ages on this question. As long as you've got it sealed, you've labelled it correctly, that's all that really matters in this question. To get the 2 marks for the question though, you get 1 mark for your Buchner flask being correct and 1 mark for your Buchner funnel being correct. Part B. This part is about amines. Part 1. The table shows the structures and boiling points of 3 amines, which are structural isomers of C3H9N. Explain the difference in the boiling points of the 3 amines. So firstly with this question, let's start by looking at the amine with the highest boiling point. So we can draw it out and we notice that it's got no branches, and that means that it's got more points of contact or more surface interactions. So this also means that it's going to have stronger induced dipole-dipole interactions or London forces. All the amines will have these induced dipole-dipole interactions, but this first amine, the one with the highest boiling point, is going to have the strongest induced dipole-dipole or London forces. So then we can start to look at the differences between amines 1 and 2, and then this huge jump to amine 3. So this huge jump is due to hydrogen bonding. So amines 1 and 2 can both hydrogen bond, and that's because the nitrogen has this lone pair that's accessible. Whereas this third amine, the nitrogen lone pair, isn't accessible. It can't form these hydrogen bonds, which is why its boiling point is so much lower than the other 2. And the reason between the first 2, the differences, is because of this induced dipole-dipole interactions. Then if we look at the hydrogen bondings and just write a quick little statement, that's that hydrogen bonds are stronger than London forces, and so more energy is needed to break the hydrogen bonds. So that's why there's this huge difference between 2 and 3, and then the difference between 1 and 2 is just London forces and branch chains. To get the 4 marks for this question, you get a mark for the comparison of branching and points of contact, so saying that there's no branches in amine 1. Then you get a mark for the relative strength of force, so saying that amine 1 is going to have stronger induced dipole-dipole interactions. You get a mark for saying that amines 1 and 2 can form hydrogen bonds, or that amine 3 can't form hydrogen bonds, gets you your 3rd mark. And you get your 4th mark for saying that you've got the relative force of the hydrogen bonds and that you need more energy to break them. Part 2. Amine A is a liquid at room temperature and pressure. When vaporized, 0.202 grams of the amine produces 72.0 centimeters cubed of gas at 1.00 times 10 to the 5 pascals and 100 degrees Celsius. The carbon-13 NMR spectrum of amine A has 3 peaks. Determine the molecular formula of A and suggest a possible structure of amine A. So let's start by highlighting the key pieces of information in this question. So that's the mass of the amine, the volume of gas and the pressure, the temperature, and that the carbon-13 NMR spectrum has 3 peaks. So there are 2 equations we're going to be using in this question, and our first one is the ideal gas equation of PV equals nRT. So we're going to rearrange to work out moles, and then we're going to use a second equation, or an equation triangle, of mass is equal to the number of moles times the relative formula mass. So firstly, rearranging for moles for the ideal gas equation, that's N is equal to PV over RT. And then we can use a list method to work out what information we have and which we need to work out. So R is the ideal gas constant, and that's 8.314, and that's in your data booklet. Then V is 72 times 10 to the negative 6, and that's because you're converting centimetres cubed into metres cubed. And then temperature needs to be in Kelvin, so it's going to be 373 Kelvin because we've added 273 to 100. Then we can work out P, well, we're already given it, it's 1.00 times 10 to the 5 pascals. So now we can plug this into our rearranged equation for N. So N is equal to 1.00 times 10 to the 5 multiplied by 72 times 10 to the negative 6 divided by 8.314 multiplied by 373. So N is equal to 2.32 times 10 to the negative 3 moles if we plug that into the calculator. Then, using our equation triangle, we can work out the relative formula mass. So that's going to be 0.202, which is the mass of the amine that we're given in the question, divided by the moles. So 2.32 times 10 to the negative 3, and that equals 87. So in the amine, we know we've got carbon, we know we've got hydrogen, and we know we've got nitrogen. So we can work out the molecular formula. So the relative atomic mass of carbon is 12, of hydrogen it's 1, and nitrogen is 14. And using these numbers, we determine that the molecular formula is C5H13 and N. So to double check, we can do 5 times 12 plus 13 plus 14, and that's going to equal 87. So that's just a way to double check. So now we can write the molecular formula on the line, so C5H13 and N. There are several different structures of A that are accepted. As long as you have 3 peaks in a carbon-13 NMR, they will allow it. So an example of an allowed structure here, we have a symmetrical amine, and if we label the carbon-13 peaks, we have 1, 2, and 3. So 2 and 1, it's symmetrical, so you can draw a line down the middle to help when numbering your carbon environments. Other examples of accepted structures I will draw now. So here's our first alternative. As long as you have 3 carbon environments, here we've got 1, 2, and then 3. Another allowed structure is similar to the one that we've drawn here, but instead of the nitrogen being in the middle, it's going to be a side group. And we have 1, 2, 3, 2, 1 carbon environments. Alternatively, you can have 3 on the side, like 3 methyl groups on the side here, and then you have your NH2, or you can draw it like this with the NH in the middle and then another methyl group coming off. But you would have 1, 2, 3 carbon environments and 1, 2, 3 carbon environments in your carbon-13 NMR spectrum. So all of these are allowed. There are others, but these are the 5 that the mark scheme has, and they're the most common that they will allow. So in order to get the 6 marks for this question, you get a mark for rearranging the ideal gas law to work out moles. You get a mark for plugging in the correct values into this rearranged format. You get a mark for your number of moles, so 2.32 times 10 to the negative 3 moles. That gets you a 3rd mark. Then you get your 4th mark for calculating 87 as the relative formula mass. You get your 5th mark for working out the molecular formula from this relative formula mass. And then you get your 6th mark for your proposed structure of A. Part C. The amino acid ZH2N CH-CH-COOH can react to form a cyclic compound with the molecular formula C3H3NO and one other product. Complete the equation for this reaction. So the key in this question is that we're forming a cyclic compound with the molecular formula of C3H3NO. So what happens when you react an amine, which is this NH2, with a carboxylic acid, which is this COOH, is that you're going to form an amide. So the general structure of an amide is NH2, and then you're connected to a carbon R group with an R group attached. You can have other R groups, so you could replace these 2 hydrogens with R1 and R2, and this could become R3. But it's this nitrogen attached to a carbon R group. That is what an amide is. So now we need to think about how we make this cyclic. Well, the purple and the green groups are going to bond together and make a square, which is going to be our cyclic compound. So here we're going to have NH, and then that's going to be bonded to this carbonyl group, so C double bonded oxygen, but the rest of the structure is going to stay the same. So we're still going to have this double bond, and we're still going to have our 2 hydrogens. Now we need to work out what the other product is, and there's only one other product. So the way we can work this out is looking at what we've lost. Well, we've lost one of these hydrogens, and we've lost an OH. So a hydrogen plus OH, well, that's H2O. So that's going to be our second product. If you're ever unsure, just look back at your reactant and you'll look at your product and see what's missing, what's changed, and that's going to be your other product. So to get the 2 marks for this question, you get 1 mark for your cyclic compound and 1 mark for water.